Okay, class, so welcome back. Let me say where we were last time, or the last two times. So we introduced the notion of a vector space and gave some of its properties. Okay. And then we really started working with linear combinations. Okay, so this was just kind of the basic operation that you were allowed to do in a vector space. You're allowed to take any vector or any two vectors. You're allowed to add them together to make a new one. And then you are allowed to also multiply by a scalar. Right? So this would be v and this would be alpha v. Okay, and then you take various sums of these, and that generally that was what was a linear combination. And then we saw the idea of a basis for v. So this was just, well, a special subset of v, which I won't write out the definition again, but the essential characterization is that any vector in v was some linear combination of vectors in this basis, right? So this is v1 up through vn. Okay, so now we're going to kind of get really more into the heart of the class. So vector spaces are obviously important part of the class, but what we really want to study is not just vector spaces on their own, but rather their symmetries. So we are most interested in studying the symmetries of a vector space. Rather than the vector space itself. Okay, so why is this? Well, so it turns out that in some sense, vector spaces are rather boring objects to study. Okay, so why would I say that? Well, here's like a boring fact. Okay. Take any vector, let's just say V is a real vector space. Which sends, with a distinguished basis, okay, so with basis, so I'm assuming it's finite dimensional, which just means that this basis is a finite set. Okay, so I have a basis v1 and 3 vn. Okay, then there is an obvious map. Okay, from Rn, and that's just because I chose it to be a real vector space, to V. And what does this do? Well, it takes Rn. Now remember, Rn has a usual coordinate basis of just, zeros in one coordinate and 1 in the ith. Okay, so maybe I'll put this here. This was 0, 1, 0, and this was the ith slot. Okay, so you send this to V sub I. Okay, and then you do what's called extending linearly. So this is just a nice kind of tool to know. Anytime you have this assignment of one basis element to another basis element, you just declare, well, where do I send any V? So where, or maybe I'll change it. So where to send, what do I call this? R? It's not a good real number word, but okay. Where to send R in R? Well, R is equal to alpha 1 E1 plus alpha 2 E2 up through alpha n En. And where do you send R? Well, you just send it to the linear combination of the VI's using the same scalars. Okay, so you send f, I'll call this function f. So f of r is just alpha 1 v1 plus alpha 2 v2 plus alpha n vn. Okay? So, and this map, since vi is a basis, this map is a bijection. Okay, so in some sense, v is, exactly the same as r. Okay. Okay. So in other words, when I'm looking at v, I've picked my favorite basis vi. Well, that's really if I start doing operations using these coordinates, it's the same exact thing as working with Rn with these standard coordinates, right? You're just you're changing the labels from EI to VI, okay? So this is, kind of depressing, right? That basically, if I take this real vector space, I pick a basis, then I'm basically working with Rn, just changing the labels. So maybe I'll mention this is, it is still useful to think about other vector spaces. Okay, so for example, let me just give specific example. Okay, of like one of our favorite examples, polynomials. Okay, so the vector space of polynomials with real coefficients and degree less than or equal to n. Now remember, this does have a standard basis. I mean, again, there's always a lot of bases floating around, and maybe at some point I should probably mention other interesting bases for the space of polynomials, but the standard basis was the monomials. So every polynomial is a0 plus a1t up to plus antn, t to the n. Okay, and the basis of for this polynomials was just to set 1t squared up to t to the n. Okay, so then we do have, just as I said before, we have this bijection between the polynomials with real coefficients, and Rn just sends the first coordinate to 1, second coordinate to t, third coordinate to t squared, and so on. Okay? But why would we ever consider this vector space of polynomials instead of working with Rn? Well, here's, one reason, and there's a lot of reasons, okay, but here's one. If you have a subspace, or I'm going to say there's maybe a natural subspace of p to the n. Again, there's going to be a lot of natural subspaces, okay, but I'm picking one randomly. We can just say this are, functions of degree less than n, where let's just say f of 0 is equal to 0, and f prime of 1 is equal to 0. Okay? So polynomials whose value is 0 and the derivative at 1 is also 0. Okay? So maybe I'll leave this as an exercise. Maybe I'll call this something. I don't know. X. Okay? Check that X itself is a vector space. Okay, hopefully I set it up correctly. Meaning that that if you take two polynomials and take their sum or multiply by a scalar, you still get the same quantity. Okay? or you still stay in X. Okay, so that turns out to be true. And the point is now that, so it's simple to define, and also we have kind of a geometric picture of, what elements in X in this subspace look like, right? They're polynomials where that they do something. They have degree less than n, I guess. That's also important. But they pass through 0 at 0, and at 1, they have local max or local min. Okay? So this is something that's very easy and natural to define. If you think about the space of polynomials, we have this nice geometric picture. Well, now just, go to Rn and just think about this subspace. It's also, you can use this bijection backwards to think about X as, some collection of vectors in Rn. Well, now you don't really have any good geometric feel of what X is anymore, right? Or, well, maybe you can, but this is certainly far more natural to think about, right? Just all polynomials with these two properties, okay? So that's one reason to consider other vector spaces, even if they're all kind of naturally in bijective correspondence, okay? But in general, you get a much richer structure, more interesting objects to study when studying the symmetries of a space rather than the space itself. Okay, so let me just, before getting too much into it, let me give you a kind of the first example of this, right? Let me just say if I have a set X with n elements. Okay, this is like the just one of the most basic objects that you have. Okay, so you just have, and you don't know anything about it, no other structure at all. Okay, so what can you do with this? I tell you, you have a set with n elements. What can you do? Well, not much. Okay, that would be my inclination, at least, right? I pick out, essentially, it's, 0, 1, 2, n minus 1, okay, because I wanted to pick n elements. This is my set. I can't really do much with it, okay? On the other hand, what I could look at is the symmetries of my set. Okay, so what would a symmetry be? Well, this could be the set of bijections. I mean, I could look at functions from x to x. Let me just, from now, stick to bijections, which go from x to itself. Okay, so that's something I can do with a set. And this I'm calling a symmetry of the set. Any permutation of these n elements. So i.e., this is called the permutation of, so all permutations of n elements. Okay, and I claim, I'm going to claim without proof that this is a much more kind of richer object. So one reason that it's richer, so this has more structure than X, because I can compose. So I can compose two bijections, so F composed with G. Okay, and this is still a bijection from X to itself. Okay, so going from, by looking at the symmetries of the space, I'm essentially going from a set with absolutely no structure, right? I don't know a thing about this thing, about X, to another set, like I could just look at the set of all bijections. Maybe I should say this is, if you want to Google, this is called the symmetric group, SN, and I would Google it. It's kind of a ubiquitous object in mathematics just because it, it comes from such a fundamental or place, okay? So it has more structure, so I could look at this set, and now I also get this operation, right? And once I have this, well, this naturally leads to a lot more interesting questions and things to study, okay? So moral, better to study card shuffling rather than the cards. Okay, right, X could be a set with 52 elements, and I'm basically thinking of it as a set of cards. Well, it's more interesting to study how you can shuffle cards rather than studying the cards themselves, or itself. Okay. Anyways, so for this class, we don't just have a set, right? We have a set with additional structure, right? We're looking at vector spaces, not just arbitrary sets. So here's kind of the philosophy here. Which works more generally. Okay, so given two sets, X and Y, with some additional structure, okay? So in general, this can be pretty, varied. It might be an operation on a set or a distinguished element like 0 or 1. And with additional structure, what we want to do is we want to consider the functions from X to Y which preserve this structure. Okay, so this is, I guess, usually called a morphism from X to Y. Okay, so you could think in the last example, the only structure was that the set had n elements, so we had to assume that its image had n elements as well. Here we have a vector space structure, so that's naturally what we want to preserve under this function. Okay, so let me give you kind of a non-example first, something that this doesn't work for, a function that doesn't fit this philosophy. Well, if I go from R to R, and I send x to x squared plus 1, well, so for one thing, this kind of fails all our characteristics, right, of what we might want. Right? For one thing, f of 0 is not equal to 0. So that's bad if you want to kind of preserve additive identity. F of 1 isn't 1 if you want to preserve multiplication. In general, if I have f of x plus y, right, so I take a sum, well, it's not f of x plus f of y. And same for multiplication. Oops, I think I flipped those, but okay, still works. Right, so, if I want to preserve somehow addition, well, here it matters whether I, add two things and then plug into f, or plug them both into f and then add them. Okay, so addition, multiplication are preserved. This is something, this is a perfectly interesting function, but not something that we're going to be interested in studying in this course. Okay, so let me give you an example. Okay, that's better than a non-example. So this one will require the complex numbers. Okay, so I'm just gonna, even though I haven't really defined them, I'm not going to use very much. Okay, so there's a special function from the complex numbers, which is called a complex conjugation, and it just sends z to what's called the conjugate. So if z is equal to x plus iy, this is just x minus iy, okay? So it sends the complex number x plus iy, it just reflects over the horizontal axis to xi minus iy. And you can check, and this is kind of a good exercise if you want to check your complex addition and multiplication. Well, if you take the complex conjugate of a plus b, this is equal to the conjugate of a and b. This isn't complex addition is just vector addition in R2, and this is obviously preserved if you flip over the x-axis. Okay. But more, strikingly, it's also the fact that if you take two complex numbers and conjugate, it's exactly the same as conjugating first and then complex multiplying. Okay? So this would be what's called, also I should say it sends 0 to 0, sends 1 to 1. So this is what's called a field automorphism. Okay, you don't need that isn't necessary knowledge, but this is just the general idea. So first, automorphism means it's a morphism, which is a bijection, and the word field in front tells you that it preserves all the structure of a field. Okay, so that the complex numbers have this addition, multiplication, 0 and 1. Those are the important things. And conjugation preserves this. Okay, so that's a symmetry which kind of preserves the field structure. Okay, so this also, let me give you another example. So this philosophy, of course, depends on what structures you want to preserve. Okay, so for example, if I take, maybe I'll call this minus 1 from z to z, which just sends x to negative x, then this does preserve addition, right? So if I take x plus y and negate it, this is negative x plus negative y. On the other hand, it doesn't preserve, but not multiplication. Okay, so it's not true that negative xy is negative x times negative y. Okay, so what this means is it just, this is a function perfectly good, and you just have to kind of, recognize what's preserved under this and what isn't. Okay, so this, I guess, would be called a ring automorphism rather than field automorphism. Well, z isn't a field. Okay, so what do we want to do for vector spaces? Let me maybe push this up. Okay. So for vector spaces, we have two things. Which are kind of encapsulated in this notion of linear combination, right? We can add vectors, we can multiply by scalars, okay? So we want to preserve linear combinations. Okay, so here's kind of a definition. This is really like a definition, I would say, of the quarter. Kind of the most important definition that we'll see. Okay, so V and W are going to be vector spaces. And maybe, I just want to, so T from V to W is linear, or a linear transformation is another. Linear function, linear transformation. These are all acceptable terminology. Okay, and maybe I just want to pause here. So try to write down the definition yourself before I tell you, knowing that what it has to do is preserve the scalar multiplication, preserve addition. Okay, so preserve these linear combinations. Okay, so I will pause here. Okay, so the definition, maybe I'll add another f, since it's if and only if. So this is, well, just t, and I put in a linear combination. Okay, so this is just an element of v, is equal to alpha 1 t of v1 plus alpha 2 t of v2 up to alpha n t of vn. Okay, so maybe I should have said, certainly, this doesn't make sense if they're vector spaces over different fields. So over the same field, okay, so then these are all elements of W. I can take scalar multiples, so I get an element of W. Okay, so here I'm going to leave this as an exercise. I mean, there are other ways to define this. So this is linear, is linear if and only if, well, you plug in any sum and you get the sum of the images and you multiply by a scalar and it's the same as taking the image and multiplying by a scalar. Okay, so there's a pretty easy induction proof to go back and forth between those. Okay, so let me give you some examples of linear transformations. Okay, what is kind of the first example? Well, what you can do is any two vector spaces, just send any vector v to 0. Okay, so the 0 map, which I'll say, okay, just taking every vector to this distinguished element 0, and your range is a linear transformation. Okay, I won't prove any of these, but you should kind of think about why this should be true. In this case, it's just, well, both sides, everything is 0. Okay, another one which you can only define if you have the same vector space is just v goes to v. So these are kind of the two kind of trivial linear transformations. Okay, so this is called the identity. Sorry, not the trivial map. Again, we see non-examples. Which go, something like, I mean, anything which will end up being a quadratic is going to end up not being good. So x to x squared is not a good example. One that we've seen before today, I guess, and even in the couple lectures before, was the derivative map. So V was the space of polynomials of degree at most n. W is the degree of polynomials at most n minus 1. Then T is just taking the derivative. Okay. Then what I get is T is a transformation from polynomials to with a degree at most n to polynomials to degree n minus 1, and it's linear. Okay, so we know that the derivative of f plus g is the sum of the derivatives, and the derivative of a product, or sorry, multiplying by a scalar multiple is equal to c times the derivative. So maybe that's a good, another thing you can do with polynomials, of course, is multiply them. Right? But notice the derivative of a product is not the product of the derivatives. Okay, so something more interesting is going on there when you start multiplying polynomials. Okay, so maybe I know we haven't seen very many examples. I'm gonna do some more, okay? But I think I wanna first just say a lemma, because it will make the examples a little easier to work with, okay? Or at least let me kind of do some tricks for showing things are linear. So the lemma states that compositions of linear transformations are linear, okay? Which I won't prove this. So this is linear. T prime from W to U is linear. This implies that the composition is linear. Oops. I think that is the wrong letters. Let's see. V to U is linear. Okay, so I mean, and this is really not so hard to show. I'm going to leave the proof for you as an exercise. Okay. I mean, essentially, you have a linear combination. A linear combination here goes to a linear combination here. A linear combination here goes to a linear combination here. So you just compose and you'll get some, kind of more complicated linear combination, which will still be preserved. Okay? So that's basically the reason that's true. Okay, so let me give you kind of, this is still a kind of shocking example for me. I mean, when I first learned of some linear algebra, or maybe this, I forget when I was shocked, but at some point I was shocked that rotations were linear. Okay, so this is a function from R to R2, and you rotate the plane around the origin by some number. Okay, so I'll just say alpha. Okay, without even giving like units or anything, just you do a rotation. Okay, sorry, I realized I should have said something a little bit back, and I'm just going to put it in here. I don't think it's too bad to put it here. So notice that for any linear transformation, so if t from V to W is linear, this implies that t of 0 in V is 0 in W. Okay? So in particular, this is why I have to rotate around the origin. Okay? So I'm fixing 0. If I do some other rotation, around another point, it's not going to be a linear transformation. Okay? So why is this linear? So why linear? Oh, sorry. Put this up here. Okay, well, so what you have to check is that if you take two vectors and you take their sum, so this is V1, V2, here's V1 plus V2, then you want to rotate. I don't know how much I'm rotating by. Let's see, is this picture okay? This is T of V2. Okay, some of my lengths got raised in in doing this. Okay, so you want to show that the sum, that t of v1 plus v2 is equal to t of v1 plus v2. Okay, but notice when you do this rotation, this parallelogram just gets taken to another parallelogram of exactly the same size. Okay, so the parallelogram gets rotated. Okay, so when I take this sum and I get to this, I look at the sum of these values and then rotate, it's obviously the same as rotating and then taking the sum, because you're rotating the entire parallelogram. Okay, so this is one of these kind of, working out this with equations is terrible. You can do it, okay, so working with the equations is bad here. So trying to write down, what this rotation is actually doing to all these points, I'm not going to bother with. The picture is the one to keep in mind. You're just preserving this parallelogram. In the same vein, if I take a vector, I scalar multiply. Somehow my scalars are always bigger than 1. I should at some point remember to multiply by something less than 1, or maybe a negative number. Okay, so you should probably do that, try doing that for your own pictures. Anyways, if I rotate v to a vector, well, and then certainly if I rotate alpha v, I'm rotating to exactly the same place, but again, just multiply by alpha. Okay, so when you take this scalar and multiply and then rotate, it's the same as rotating and then multiplying by this scalar. Okay, so rotations, which at least to me did not seem like a very linear object, turn out to be linear transformations as long as they're rotated around the origin. So another good one is reflections. Again, these are transformations from R2 to R2, and they have to be across lines through the origin. Okay, so let me just pick a line. I guess pick the what's called the anti-diagonal. Okay, what is reflection over this line? I'm just going to call it H. Okay, well, you pick any point. You draw the line orthogonal passing through that point and orthogonal to the hyperplane, or to the line, and then draw the same distance on the other side. So these are equidistant. This would be v. This would be t of v. Okay, so notice again, since the reflection is through the origin, t of 0 is 0. Okay, that's why you can't reflect over the line x equals 1. That's that wouldn't preserve 0. Okay. So here I want to show that this is linear. Again, I don't want to ever actually do an explicit formula, especially since I don't really know what h is. Okay. So I want to present, I think, kind of a useful trick for showing why this reflection is also linear. Okay. So you know what, and I'm going to, F was just a terrible choice of, let me see, I'm going to erase this. F is just a bad letter to use. I'm just using it too much, so let me just call this RH, okay? So reflection over the line H passing through the origin. Okay, so why linear? Well, notice that reflection over H is exactly the same. So as a function from R2 to R2, as first rotating h to the x-axis. Okay. And I just chose the x-axis just for ease. You could rotate to the y-axis if you want. Okay, so you do this rotation by some number of degrees alpha. Then reflecting over the x-axis. And then rotating back. Okay, so rotating that direction alpha, then rotating back. Okay, so you should, this is a good thing to kind of try to work out and convince yourself that these are the same functions, okay? I mean, the first thing to check is that if you take a point on h, then this should be fixed under this procedure, right? Since the reflection fixes h. Well, it's also true that if I take this to the x-axis, reflect over the x-axis, and then rotate back, it also fixes points on h. Okay, so it turns out that these are exactly the same operation, but I would, draw a couple more pictures or check a couple more points so you can see what actually is going on. Okay, so therefore, what I'm saying here now is that RH from R2 to R2 is a composition. Okay, so maybe I'll just write it as you rotate, let's see, so what do we first do? So you first rotate by alpha, I guess. Then you reflect over the x-axis. And then you rotate by negative alpha. Okay, well this one is very easy to check whether it's linear, right? This just sends x1 to x1. It sends x2 to minus x2. And it's easy to see that this operation will be a linear transformation. Okay. Therefore, since we already worked out that rotations, and I should say you're rotating around the origin in both of these, so this is going to be linear. You have two rotations which are also linear. Well, therefore, what's going to happen is their composition is a linear function. Okay, so the composition is linear. Okay, so this is just, I think, a good, useful trick for whenever you want to figure out some sort of formula or work out some properties of a function. You can often write it as a composition of simpler functions that you understand, okay? And then you hope that if you understand these functions well enough and you understand how their composition works, you get a better feeling for what your function is actually doing, okay? So this is a useful trick, which just comes up all the time. Decompose a function into simpler components. I mean, you can argue here whether a reflection is kind of simpler than a rotation, but, we already kind of worked out what these are, okay? And then this is certainly simpler than an arbitrary reflection over a line. Okay, so let me do, I think I want to do two more examples, and then we'll be done. So let me give you two more examples, actually characterizations. Okay, so first, what are the linear transformations from R to R? Okay, thought of as real vector spaces. So Well, there's kind of there's always the first one, right? You could just send everything to 0. So f of x is 0 for all x. That's obviously okay. What are the other options? Well, notice given any linear transformation f, well, I have 1 goes to f of 1. But notice now I know exactly where any x goes, right? So x, I'm thinking of x times 1. So I guess here I'm thinking of x as scalar, here I'm thinking of it as a vector. Then f of x is x times f of 1, okay, by being linear. So therefore, you just get functions f of x is mx, okay? So not surprisingly, these are all the linear transformations from R to R, okay, just multiplying by a scalar. So let's think about what linear transformations from R2 to itself look like. Okay? So we know, so take a v and v. We're going to do a similar trick. We know v is equal to alpha 1 e1 plus alpha 2 e2. So therefore, f of v is equal to f of alpha 1 e1 plus alpha 2 e2. And by linearity, this is alpha 1 f of e1 plus alpha 2 f of e2. Okay? Where I'll just make it explicit. e1 here is 1, 0. e2 is 0, 1. Of course, I didn't have to. I could have chosen a different basis for R2, but I'm choosing the standard one just for now. Okay? So therefore, I mean, these are just, these are two vectors in R2. And therefore, we know kind of, if we know what v is in these coordinates, if you can work out what the images are, then you know essentially the entire function. Okay, so f is determined by f of v1 and f of v2. Okay, and f of v1 and f of v2 are arbitrary. Okay. Okay, so you can just send them kind of anywhere, and then the rest of the function is determined. Okay, so here's maybe the example. We're taking e1, e2. It's usually helpful to draw this box here. Well, a linear transformation, we'll send f of v1 here, f of v2 here. Okay, and then, so the box goes here. And then any other vector that you're interested in, well, you take, this one, well, it's this much of e1 plus this much of e2, and then you just plug that into, take the exact same amount of this vector plus the exact same amount of that vector. Okay, so it's determined essentially by the image of these two vectors. So notice I could have something. Well, I could send everything to 0. I could have also sent them, to the same line. They don't need to be distinct vectors, or they could be scalar multiples of another. That would be fine. And then just the image would be completely contained on the line through the origin. Okay. So let me see. I'm just gonna, since it's already 50 minutes, I'm just gonna end with a deep fact, which I think is really remarkable. I'll do it, for, I guess, for Rn to Rn. Let's just say I take Rn. I mean, if you want like some sort of characterization of what these linear transformations actually are, this is a hard fact to show. But if you take a bijection, and it takes lines through 0 to lines through 0, okay, we know that this is what linear transformations are going to do. Okay, so it's going to take any line through 0 to another line through 0. This is linear. Okay, so if it's a bijection and it has this property, it implies f is a linear transformation. Okay, so that's kind of, I mean, a geometric picture of what you can imagine is going on here, right? So as long as you take any function from Rn to itself, it just preserves these lines through the origin. That's a linear function. That's what we're dealing with. Okay, so went a little longer today, but thanks.